course.
Thank you very much.
The Quadratic Foundation is actually connected more or less to the high-rise buildings, and as you can see from this slide, in most of big cities all over the world, we construct more and more high-rise buildings. Frankfurt, New York, Hong Kong, where we have actually demand due to the lack of suitable area for the construction of high-rise buildings, or sometimes you construct high-rise buildings in Sahara, like in Dubai or in Jeddah. The highest high-rise building is now under construction in Jeddah in Saudi Arabia, and this is more or less not for a need of lack of construction area. Maybe not more than 10 to 15%, but the construction time of the foundation is actually the main problem. Sometimes it is more than 30 to 50% of the total time of construction. Therefore, this makes the foundation of high-rise building interested for us to save time, and if we can save also money, why not? And this was actually the start of the story of high-rise building in Frankfurt. In the last century, say 60s, 70s years of last century, we have applied conventional raft foundation up to a height of about 100 meters with a lot of measures to control the settlement. After that, we have applied the conventional raft foundation if it is possible. This is the middle figure here. And within the time, we have developed the raft foundation as the most economic and fast foundation methodology. Below it, we have limestone. Therefore, if we apply in such case here conventional deep foundation, the pipe should be more than 100 meters longer, and this, of course, not very suitable and not economic. The idea of Quadratic Foundation is very simple. We say if we have conventional raft foundation, then the total load of the superstructure QT and the load of the piles, in this case raft foundation load of the piles, is equal to 0. Then the factor alpha L will be equal to 0, and then we have conventional or traditional raft foundation, and we have maximum settlement. The settlement will be exactly equal to the settlement of raft without piles. And if we have conventional pile foundation, when we assume that the total load is taken by the piles, then the alpha L factor QB divided by total load will be equal to 1, and the settlement will be smaller than that of traditional raft foundation. The bandwidth of the settlement will depend on the number of piles, pile length, pile diameter, and so on. Our pile raft foundation is in between, where we assume that the contact between the raft and the direct soil, this contact can take part of the load. Of course, this is very logic, and so long we pour the raft directly on the soil, we can assume that part of the load will be taken directly by the soil. Only in conventional analysis, we don't consider this part of the load. Now we have more advanced technical and softwares and constructive laws to model the soil structure interaction and to calculate this part. Therefore, what we know now is not more than we apply something which is already invented in the system. We try to use the part that taken directly by the raft. But why we have such long time needed to develop the pipe raft foundation is actually the nature of the pipe raft. It is a very complex soil structure interaction between the structure, the raft, the piles, between the piles and the raft, and this mutual interaction make this system very complicated, and then we need really very complex finite element analysis, mainly three-dimensional finite element analysis, and till the end of the last century, it was very difficult to carry out such analysis. Now, with the development of software and of the computer capacity, it is very easy, and it is more or less now daily work of us to apply three-dimensional finite element, and this gives us the possibility to apply the pipe raft in a very wide scope. The second problem with the pipe raft foundation is the codes. Till also maybe about 15, 20 years ago, it was not allowed to apply this load part taken by the raft. And in Germany, they have applied the pipe raft in the first 20, 30 years on their own responsibility, without coding, without codes, without recommendation. And after that, we have developed the recommendations, which is the German recommendation for the application of pipe raft foundation. And this recommendation is now referred to it in the Eurocode. And we can say now that the pipe raft is accepted by the Eurocode, and this has also increased the amount of its application all over the world in the last 2 decades. This figure shows something about the history of pipe raft foundation in Germany, in Frankfurt. And in the right-hand side graphs, you can see that very nice, realistic figure. It is actually from measurements between the so-called alpha L, the load factor taken by the piles divided by the total load of the superstructure, and actually measured settlement for some high-rise buildings in Frankfurt. And you see, in case alpha L equal to 0, that means we have conventional raft foundation. We have applied high-rise building on raft with settlement between 10 to up to 30 centimeter. 30 centimeter, can you imagine that? In most of codes, people say not more than 5 centimeter or 10 centimeter for raft foundations, and we apply here settlement up to 30 centimeter, and all this building is still in very good conditions till today in Frankfurt. And then come the new generation where we have applied pipe raft foundation, and you can see that by the idea using pipe raft foundation, we have controlled the settlement, and the maximum measured settlement was less than 15 centimeter. Also relatively higher than what we can imagine in other standards, but it's actually the basic idea that total settlement should not be our main problem. Our main problem is the differential settlement and the tilting of the building, and the effect of the settlement and tilting on the utilities connecting the building with the general utilities come from outside, or on the internal architectural elements and mechanical elements like lifts or windows of high-rise buildings. Therefore, in high-rise building, the most important point beside the total stability and factor of safety, of course, ultimate limit state, is the serviceability limit state. And for such huge buildings and huge loads, we cannot consider settlement and differential settlement as in ordinary structures. We should check it case by case, and really we can say there is no limits. Most important is actually the performance of the building, and this is what we have applied successfully in Frankfurt clay. The history started in the 80s, in the last century, for such building, and it was a shallow building. There was no basement, and the building is divided in 2 parts, due to the existing of sewer pipe, main sewer pipe in this road beneath the building, in the middle of the building. Therefore, they have said, okay, we will apply pipe foundation. and the thickness of the clay is too deep. Therefore, they say, okay, we will apply the idea of pile draft foundation, applying very simple calculation methodologies at this time. Therefore, they have done a lot of measurements, and this was actually a very nice case for the observational method according to the Eurocode. We use the good engineering judgment in the design stage. We put a lot of measurements, and from these measurements, we learn what is actually the real performance of the building, and then we can improve our design for the next project and so on. And they have applied a lot of measurements, but what they have measured was actually very interesting. They have said we apply pile draft foundation. That means the piles take only part of the load, but what we measure is actually that the piles take more than 80% of the load, and only 20% of the load taken by the raft. And this 20% is not more or less is actually the own weight of the raft. More than that, they measure the load on the pile heads, and you can see that very nice Mosalamy distribution of loads. And there is high load concentration at the corner piles, at the edge piles, and the piles in the center have very small loads, although all piles have the same diameter and the same length. Therefore, we see that this was not the best pile draft foundation. Of course, it is safe. The structure is still in Frankfurt till today. You can see it when you visit Frankfurt. But it was not the most intelligent solution. And only from this observation, one go to the next pile draft foundation in Frankfurt, the Messeturm in Frankfurt. It is about 250-meter high-rise building, and for a long time it was the highest high-rise building in Europe. And without any very complex calculation analysis, but only from the observations that one has taken by the tour house, one has said, okay, if the piles at the edges attract more load due to this Mosalamy distribution at the edges, then we make the pile at the edges shorter than the pile in the middle, so that we try to have the pile more or less with the same stiffness. And if the piles exactly in the middle take not a lot of load, then we don't need piles in the middle. Therefore, we can make the no piles in the middle of the building, and we put the piles only around the shear walls, the core of the building, and then we can also control the straining action of the raft. And all these piles are floating piles in Frankfurt clay, and then they have done again a lot of measurements in cooperation with the university, the Darmstadt University in Germany. Darmstadt is about 50-60 kilometers south of Frankfurt, and the measurement has shown that now 55% of the load is taken by the raft, and 45% of the load taken by the raft, and 55 by the piles. Again, very nice load distribution between the piles and the raft, and a real nice pile draft foundation. We have done a lot of measurements in this case. Is actually the load distribution among each pile, intermediate pile, and center pile, and now you see that all piles have more or less the same load. The skin friction was a wonderful result, that the skin friction developed from pile base to the pile top, and the skin friction at the pile or near the pile base under working loads is about 160 kilopascal. From our pilot tests on single piles in the same soil, we have found that the ultimate skin friction is only 60 to 80 kilopascal. Now we measure about 3 times higher skin friction. That means there is big difference between the performance of the piles as a single pile and the same pile as an element in the pile draft foundation. And the next question, why we have such high skin friction, ultimate limit skin friction of the piles in pile groups of pile draft foundation are higher than that of the single pile. And at that stage, we have started our analysis and our numerical modeling to try to understand all these phenomena. And this starts with this building, the DG Bank in Frankfurt. It was about 200-meter high-rise building with the tower. The wind system is taken tube in tube, and therefore we have wood piles only beneath the two tubes which resist the wind loads. And there is a neighboring building, side building, which is only about 60 meters. Therefore, we have complete joint system between the tower and the side building. And we have put a lot of pile head load cells to measure the pile settlement, contact stresses, and so on. I will go very fast by how we can measure these. This is actually the pile load cell at the pile head. It is not more than two steel plates connected to each other and filled with oil, and we can measure the oil pressure by transducer, and we make calibration in the lab. Therefore, when we measure certain pressure of the oil, we can translate it directly to load on the piles, and this load cell cover the whole head of the piles. Therefore, we can measure the load during the construction and after the construction. And these are the measurements of these load cells at 6 piles in this project. This is how we can measure the contact stress between the raft and soil using pneumatic load cells that was developed in Germany, and it is now worldwide used in similar projects. And you can see that we measure here contact stress between the raft and the soil up to about 420 kilopascal. 420 kilopascal in clay. This is actually also a very high value that some people say in clay we don't like to have working stresses more than 200 kilopascal. You can see here that we can measure up to 420 kilopascal and there is no problem. This is actually how we can measure the pore water pressure inside the soil using the water measurement devices. And you can see during the construction we have done dewatering. Therefore, for the water pressure is smaller than the hydrostatic water pressure in normal conditions. And when we finish the construction of the basement and start the construction of the high-rise building, we with time reduce the amount of dewatering till we close the dewatering and we come again to the hydrostatic pressure. From all these measurements, we can see how much load is taken by the piles, how much load is taken by the raft, the uplift, and the total load of the superstructure. And you can see here now, if we make this alpha L, the load taken by the raft divided by the load taken by the total load of the structure, then we can have very nice curve, and we have here alpha L about 50%. Most important in this figure is that we have finished the high-rise building somehow here, and we have measured more than 10 years after the construction of the high-rise building, and this alpha L factor is constant with time. That means consolidation and creep of the clay doesn't affect the factor alpha L, and this is a very important design criteria. Of course, this is very special for over-consolidated clay. If we apply Quadratic Foundation in soft clay, then creep and consolidation may affect the load sharing between the raft and the piles during the lifetime of the building, and we should consider that in the design so that the string action in the raft are good covered in all conditions. This is how we can measure the skin friction along the piles by using integral strain gauge elements that we constructed ourselves in the lab, and we build it in the piles along the reinforcement gauge and then put it in the pile. Now there's a lot of companies that produce such integral strain gauges, and each body can buy it in the market. To transfer the strain gauge measurements, which is only strain to forces, to then we can calculate the skin friction, we need the E modulus of the concrete. Therefore, we use ultrasonic measurements, cross-hole measurements along the piles, and these measurements are very helpfully not only to get the E modulus of the concrete, but also to check the integrity of the piles. And then we can connect all these devices in the so-called measuring room, and then we can make the measurements during the construction and after the construction. Nowadays, we can have a modem system here with the digital system, and then the measurements can be sent automatically on the internet to your mobile or to your office, and then you can see online measurements actually for important projects. Now we go to the numerical analysis of Raft foundations, and in numerical analysis we have a lot of possibilities, but to short this part now we can only use the three-dimensional finite element analysis. Here is some results comparing the performance as calculated and as measured, and then we can understand the performance of Raft foundation. Here you can see that we can make very nice back calculation between the total load, measured load, and the measured settlement, the load share taken by the piles, the load share taken by the raft. This was for this DG bank, the last example we have discussed it. But we have done here very nice thing. We compare the load settlement curve of the pile, single pile, with the average of the pile group and with the average of the pile draft foundation compared to the measured average of the pile draft foundation. First of all, you will see relatively good agreement between the measurements and calculated performance of the pile draft foundation. This gives us confidence on our parameters. But if we compare the performance of single pile, pile group, pile draft, you find that under the same load, average load on the single pile, pile group, pile draft, the settlement is higher. That means the pile stiffness depends on the pile conditions. It is the same pile diameter, the same pile length, the same soil, the same applied load on the pile head. But if it is single pile, the settlement is smaller, the stiffness is higher. If it is the same pile but in a pile group without raft, but all piles have the same average load, the settlement is higher. That means the stiffness is smaller. And if we have the same pile in pile draft, the settlement will be higher and the stiffness will be smaller. And this is very important point. The second point is that the ultimate load of pile group is higher than that of the single pile. And in case of pile draft, we don't see any failure of the pile elements. Why? Because the raft is huge and the whole system has very high bearing capacity. And when we increase the load, we increase the vertical contact stress between the raft and the soil. We increase the confinement stresses around the pile shafts, and hence we increase the pile capacity automatically. You see here very good agreement between calculation and measurements for the load along the pile shaft or for the skin friction, and you see that the skin friction developed really from pile base to the pile top. Why? Because at the pile head, the raft is relatively rigid and it pushes both the soil and the piles with the same amount. Therefore, there is no possibility for relative movement between the pile and the soil, and hence there is no possibility to develop the skin friction. And with depth, we can build some relative movement between the pile and the soil, and hence we can develop skin friction. And at the pile base, is the maximum possible relative movement between the piles and the surrounding soil. Therefore, we have the highest skin friction. Also, the ultimate skin friction or the measured skin friction is higher than that of single pile due to the confinement around the pile, the increase of the confinement stresses due to the contact stresses between the raft and the soil. We should also consider here that the piles are about 28 meter and the raft is about 60 meter. Therefore, the piles are actually smaller than the length of the piles is smaller than the width of the raft, and hence the effect of the contact stresses between the raft and the soil is very dominant. In this case, we have only 40 piles, and you can see that with these 40 piles, we can reduce the settlement of the raft without piles from 20 centimeter to about 12 centimeter in case of wide raft foundation. And this, of course, very nice effect of the application of piles to control the settlement. Not only we have controlled the settlement, but also we control the settlement jump at the settlement joints. In case of raft, you see here the settlement jump will be about 10 centimeter. In case of wide raft, it is very small, not more than 2 or 3 centimeter. And this helps us in two ways. The first way is actually the water tightness is easier. The water stopper will not have a huge strain as if in case of conventional raft foundation. Secondly, and this was the next generation of high-rise buildings in Frankfurt, we can omit completely the need of settlement joint between the differently loaded parts of the building. And if we can have such fewer number of piles and we can arrange the piles in intelligent way below the raft, then we can actually reduce the bending moment in the raft. And this is another economical aspect of wide raft. We don't only reduce the number of piles, but also we reduce the string action in the raft. That means either we reduce the thickness of the raft or we reduce the amount of reinforcement. That means we can achieve more economic solution. And why we can reach that, this actually can be seen in this slide. You see here the contour lines of the stress distribution below the raft in case of raft foundation as well as in case of wide raft foundation. In case of raft foundation, you see here huge stress concentration just below the raft. And in case of wide raft foundation, there is completely rearrangement of the stresses below the raft. And you see that the just below the raft, the stress is smaller than in case of raft foundation. If we consider that in over-consolidated clay, also in normally consolidated clay, also in sand, the E modulus is actually stress dependent. Therefore, the E modulus increase in most our cases with depth. That means by applied wide raft foundation, we rearrange the stresses so that we don't have such huge stresses just below the raft where the E modulus is smaller. We transfer the stresses to deeper depths where we have higher E modulus of the soil, and hence this is the reason why we can control the settlements very effectively by applying fewer number of piles in case of wide raft foundation. We should also consider that in all these cases we speak about floating piles. That means the piles are in the clay layer. They don't penetrate completely the clay layer and come in other stiffer soil, but they are completely ended in the same compressible layer. Therefore, the main features of the behavior of wide raft foundation that the pile performance will depend on the pile location. There is difference between pile in the middle, pile at the edge, pile at the corner. Therefore, if I am a structural engineer and I would like to calculate the draft using structural software like SAP or SAFE, and I apply the same key value, stiffener or stiffness value for all piles, I underestimate directly or overestimate the string action of this raft. Maybe underestimate it in some areas and overestimate it in other areas. Therefore, it is very important to have a realistic distribution of the pile stiffness below the raft, either in case of traditional pile foundation or wide raft foundation. The pile capacity is completely different between single pile and pile groups or pile raft foundation, and this can be also help us to reduce the number of piles and to reach more economic solution. In the German recommendation that is now referred to it in the Eurocode, we have written that in case of wide raft foundation, we don't need to check the bearing capacity of single pile. That means actually the piles can be designed near its limit capacity. This is not more than plastic hinge in a frame action, as you know in concrete structures. The skin friction in pile raft foundation developed from pile base to pile top, and it is higher than that of a single pile due to the mutual interaction between raft and piles. And therefore, fewer number of piles can decrease the settlement very significant in case of pile raft foundation. And pile raft or piles arrangement within the pile group below pile raft foundation can be very helpful to control the string action in the raft, and hence we can reach more economical solutions. I see now that I have my 30 minutes. I don't know if we should stop now or we can complete as you like. Hello? I think nobody hear me.
Hi, Doctor. I am not sure what other people saw, but I found your presentation very, very informative, and I would prefer if you can continue, please.
Okay, in this case, we can continue maybe for about 20 minutes more. Normally, this lecture, I give it in 1.5 hours. I try to make it as compact as possible. Let us continue, and because this is online, our colleagues who have other appointments, they can leave us. After this nice experience in Frankfurt, we have started to apply this idea in other soil types and in other countries, and I will show you some interesting examples that I have shared and worked in different countries. The first was in Kuwait, and this was a very nice building in Kuwait, and the main design is with a lot of piles and longer piles, and the problem why the people come to us is that these piles transfer the upper aquifer, go through the middle layer, which is actually less permeable, and penetrate in the lower aquifer. And the environmental engineer has said, no, you are not allowed to go with your piles in the lower aquifer due to the difference of the salt content of the upper aquifer and lower aquifer. Therefore, the idea was to reduce the pile length. And when they come to us, we have seen this huge number of piles, and we have said we can optimize the solution considering both the pile number and the pile length and the pile diameter. And the soil in Kuwait is not silica sand, it is calcareous sand. And calcareous sand has nothing to do with sand, only the size, but it is actually material, carbonate material. And therefore, we have started to understand the performance of this material in tests and also in large pilot tests on the site. They have done very nice compression and tension loads, and from these loads we can define the parameters of the design, and then we go to the design and we can reduce the number of piles to this plan here. Actually, this compare the two conditions. In a case of conventional pile foundation, we have more than 1,000 piles. In our analysis, about 400 piles. The pile diameter, we have increased it from 0.9 to 1.2 under high loads. For the piles, small piles, 0.6, we have kept it. Pile length, instead of 22, it is now by us 17 meters. Therefore, we can reduce total pile length from about 24 kilometers to only about 6.7 kilometer piles. this very nice example how we can optimize the foundation of high-rise building, and we have done that for a lot of high-rise building in the Gulf countries. Now in Saudi Arabia, in Mecca, and this relatively strange why we need bite in Mecca. We know that Mecca is mainly granite rocks. Why we can need piles in Mecca? And you can see that in this case where we have a lot of valleys, which is filled with sedimented material through millions of years, and this material is mainly sand and gravel. And these are actually also very important in Mecca because it's the water resources. And these valleys go to the Zamzam in the holy mosque in Mecca. Therefore, it is for us as Muslims, it is very important and we should environmentally keep it as it. Therefore, if we would like to construct building like that on these conditions, part of the building is constructed on granite and part of it is constructed on this sedimented material, alluvial material, not more than gravel and sand. How we can construct such building, and this example is the Jabal Omar Towers in just beside the Holy Mosque in Mecca. Therefore, we make a very nice combination now. The partial of the building is conventional Raft foundation, and partial is conventional deep foundation, and then we combine them in one foundation. And then we apply also special techniques of piles. The piles are poured in stainless steel tube to prevent any contamination of the groundwater. Now we go to the next era that we develop the numerical modeling of the pile draft foundation, and I can show you example of the software Plaxis, where I have shared the development of the beam element model to model piles in this 3D analysis. What is the problem of modeling piles in 3D finite element analysis? Is the number of elements. If you model the piles as volume element, then you will find you need thousands of elements, and very closely you come to millions of elements for the whole structure. This, of course, will be a problem of the computer capacity and of the runtime. And the idea was very simple, that we model the piles as fictitious beam elements, which is connected to the surrounding soil with fictitious springs, and then we can model it in a very simple and efficient way. Then we can model very complex structure with logic number of elements, and then we can model it in logic time domain also. And we have also helped our colleagues in Poland to calibrate their model, and we have used one of the high-rise building in Frankfurt as basic for this evaluation. Most important is the soil parameters, and we have a very nice lab tests and data in Frankfurt. Therefore, we can do this calibration in very accurate manner, and you can see that we can get really very good results, and then we have high confidence on the development of these beam element or embedded beam element models in Plaxis, and these are also applied now in other softwares. With this model, I would like to show you a very interesting example in the Holy Mosque for this minaret. Again, the minaret is built partially on granite and partially in valley. This is the so-called Ibrahim Valley, and it brings water directly to Zamzam spring. Therefore, it is very important, and we should use minimum number of piles, and we have done that in a very complex three-dimensional finite element. The tower, the minaret is about 300 meters long, very slender structure. Therefore, its stability is also very important. And therefore, we have done such 3D models. modeling the igneous rock, modeling the alluvium deposit, modeling the raft. Each pile is modeled with its exact length, as we have done a borehole at each pile position to define the pile tip exactly. And we have put all of this data in the model. Then we have calculated to check the settlement and the stability performance of the whole structure. And you can see here we have settlement about 37 millimeter. And then we can calculate the pile stiffness for each pile, because each pile has different pile lengths and also different location. Therefore, each pile has its stiffness, and we have give this stiffness and the Raft contact subgrade reaction modulus to our structural engineer to complete their analysis. We have done also pile load tests, and you can see that actually we cannot see any real evidence of failure. At 4,000 kilonewton, we have less than 14 millimeter settlement. This is less than the elastic shortening of the pile material itself. Last but not the least is the highest high-rise building all over the world now in Jeddah, the Kingdom Tower in Jeddah. And Jeddah is very special because it lies just beside or on the coast of the Red Sea, and we know that the Red Sea is a huge fault, therefore it is a seismic active zone. And you see here the measured earthquake along the Red Sea. We have done a lot of site investigation. At that time, I have worked freelancer by Dar al-Handasa, and this was a project in Dar al-Handasa, and they have done a lot of pressure meter tests, and you see the E modulus of the pressure meter with depth, and you can see that it is here something which is surprise. The upper layers are very hard, very stiff, and then we have weak layer, and then another hard layer. Therefore, actually, we should bring our piles down to this layer. Therefore, the piles was really very, very long. It was longer than 100-meter piles. And to check the capacity of these piles and the huge load that will act on these piles, we have applied the so-called OC or Osterberg cell technique. We have back calculated the results to adjust our parameters and to see that all our analyses are okay. Therefore, first of all, it is very important to have good site investigation and to have very well instrumented pile load tests to go to the design of such high-rise building. This is the foundation of this high-rise building, and the building is 3 wings with huge pool, and we have put piles along the 3 wings and below the pool. You see here the 3D model that we have developed at that time. And you see that we have also used the idea that we have developed in Frankfurt for the Messeturm, that the piles below the center of the buildings are very long. Then we make the piles shorter under the wings so that we can accommodate the effect of Usenesk where we have load concentration at the edges. You see here that we have the settlement calculation, and here it was very strange that the settlement at the wings are higher than that in the middle, but it's due to the distribution of the loads, and this we have tried to make it as small as possible so that we don't have internal tension stresses inside the center core of the building. Another application with this very good beam element model that were developed in Blacksys is actually something like that in China. I have shared the design of a lot of LNG tanks in very difficult conditions in very highly seismic areas. And you can see here below this tank, which has diameter of about 60 meters, we have difference in the rock surface. From here about 20 meters, here is about 60 meters. and this is in seismic area. That means the string action in these piles will depend on the direction of the earthquake. Therefore, first of all, again, pilot test. We have done very good pilot tests, and our colleagues in China have developed this huge reaction system using this pyramid triangular steel structure and fill it with sandbags. But at the end, we can have our high loads on the piles. We have done also horizontal pile load tests. And our structural engineer modeled the tank very accurate with each beam and with each connection in the tank, and make seismic analysis to give us the PGA value of the tank. And we model only the raft with the stiffness of the tank and the piles, but in more details, the superstructure cannot model the piles. We model the piles. He can model each structure details of the tank. We simplified the tank, therefore we work together hand by hand, and then we model exactly the soil condition, the length of the piles, and apply different forces or different direction of the earthquake to check the serviceability requirements, but also to get the straining action in the piles, because the structured software cannot model actually these piles and cannot get the string action. Therefore, we have worked with very good structural engineers in Germany, in Stuttgart, and they have accepted our string action to be the basis of the design of the piles. Now we go to huge shafts in Istanbul Airport, the new Istanbul Airport, the ATC tower in Istanbul, and it is about 100-meter tower founded on rock formation, highly weathered rock formations. And then the idea was actually to found the whole tower on one huge shaft. This is the tower, and this here the shaft, and we have modeled it also here. You see huge shaft with diameter about 16 meter, depth more than 30 meter, and we apply the structural engineer calculate seismic very accurate, but at the end he gave us quasi-static horizontal forces at a certain height of the tower. That means we have here horizontal forces, moment, and vertical forces of the own weight of the tower. We model it, we check the condition under working loads without seismic effect and also with seismic effect. And you see here very nice block performance of this pier, and you see the so-called neutral level. Above the neutral level, we have on one side passive forces, in the below it we have active. In the other side, we have here tension cracks. There's no forces between the shaft and the soil, and below it we have here passive. We have very important stress distribution at the base of the shaft. You see here the neutral plane and the deformation of the shaft. And we can make our calculation to develop the stiffness, the springs that model the contact stress between the shaft and the soil at the base and along the shaft, or the friction between the shaft and the surrounding soil, and therefore our structure colleagues can further make their analysis. Therefore, actually, we can say that we cannot work alone. We work with our structural designer, our structural engineers. Normally, the work of the structure is huge and they are above us, but because we speak now about foundation, therefore I make more details for our work, and our structural engineers is here. But we have all this interface between us. We cannot work separately. We should work hand in hand. We should make site investigation, laboratory test, pilot test, back calculation from case histories. We can do a lot of work here to reach at the end realistic model of the soil and conduct our soil structure interaction analysis. What we get from all this analysis is actually two things. We check the ultimate limit state, we check the serviceability limit state. What we get our structural engineer is the pile stiffness depending on the pile position and the soil subgrade reaction modulus in case of Raft. The structural engineer conduct his analysis, and sometimes he come back and say, this pile is highly loaded, I would like to change the position of the piles, or I need here another pile, or I can eliminate this pile, and therefore we make at maximum 1 or 2 cycle iteration with our structural engineer. Therefore, actually, pile stiffness and subgrade reaction modulus are completely not soil parameters. It is only fictitious parameters that help us to cooperate with our structural engineer. Therefore, the geotechnical engineer can make his work very enhanced on very high level, and the structural engineer can make his work also on the same enhanced and very accurate conditions. And this pile stiffness and subgrade can be calculated very accurate from our geotechnical part of the work. Therefore, at the end, Quadratic Foundation can be applied in a lot and different load conditions and soil conditions. We have the so-called here, for example, uncoupled Quadratic Foundation. If I have soil where we have some swelling or some collapsibility problem, then we can make the so-called uncoupled Quadratic Foundation. We stop the piles below the raft, we don't connect it with the raft, and then we have better performance of the whole system. Piled raft can be applied to control the settlement, but also to control the straining action in the raft, or to increase the bearing capacity of the raft foundation. And at the end, I would like to thank you for your attention and for your payment, not payment, for your patience. And I hope we can see you, or we can have discussion in other opportunities. Goodbye.
Thank you very much for the nice presentation. I think Mohammed want to ask. Thank you very much. Yeah.
If anybody has questions, please, we can have some questions.
Yeah, Mohammed, you can start.
Hi, Dr. Yasser. It's a really great pleasure to hear a very interesting presentation like this from you.
Thank you.
I have a question.